No worries. Well, hello everyone. Thank you for the introduction. Let me share my screen and see if I can do that. Yeah. Okay. So can you see my screen? Okay.
No. Yes, we can.
All right. So my talk today is very relaxed. I'm coming to you from Sydney in Australia, and when I go traveling, many people say that Australians are quite relaxed. So I'm going to talk, just at a hopefully a slow and understandable pace. The mathematics that I'm going to share with you is not particularly difficult. So I'm hoping that almost everybody can understand the ideas. Okay, so you can probably see that there's a picture of Sydney there, and the dotted area is actually my university, and it's the University of New South Wales, and New South Wales is the state that Sydney is the capital. So you can see in the background there's downtown, and the Opera House is just there, and the Harbour Bridge is there. All these famous things. So when COVID disappears, I would like to invite everybody to come to Sydney at some point in the future. Come and visit me at UNSW. Some of you may have already been to Australia. If you've already been, then let me know in the comments section. One thing that we do have is very strange animals. Maybe you know some of these animals. Some of them are friendly, and some of them are not. But don't worry, I will protect you if you come and visit. All right, let's do some mathematics. So my talk, it's related to what Andrea was talking about, in a sense, with difference equations, and in particular, I'm going to talk about shooting methods and discrete boundary value problems. Okay, and now when most mathematicians think of shooting methods, they think of differential equations, right? This is sort of the history. And I thought, well, can you connect shooting methods with difference equations? And the answer is yes, you can. But the mathematics is not very complicated. Okay, so that's what I'm going to talk about today. So you get to see, my big hairy hand on the screen. All right, so I think it's fair to say that as mathematicians, we like to count, and in particular, enumeration, or the science of counting, is kind of what we do as mathematicians. And when we have an equation, there are many questions, but an important question is, well, if we have some equation, is there one solution, no solutions, or more than one solutions? And in particular, how many? Okay, if there's more than one, how many are there? Exactly, right? So what is the cardinality of the solution set? All right, so these are some of the ideas I'm gonna talk about today. All right, okay, so I'm gonna try to add some knowledge regarding the number of solutions to discrete boundary value problems, and I'm going to use this standard abbreviation, BVP. And it's not hard to construct a problem that has no solution, or one solution, or infinite number of solutions. And so is there some sort of scientific way of precisely counting the solutions? Okay, and it's possible. It is possible. Okay, it is possible. All right. So let me quickly talk about shooting methods. The main history of shooting methods is really in ordinary differential equations. Okay, you have some ordinary differential equation, some boundary value problem, and you want to approximate the solution. Okay, and you have some sort of interval, and maybe this is the end of the interval, and you shoot the solution over, and you want to try to get to some point over here that fits with your boundary conditions. Okay, so you adjust the angle or something like this, and you get all these potential solutions based on the initial value problems. And one thing that I learned a couple of years ago is that shooting methods and difference equations, not much has been written about this stuff. I could only find 2 or 3 papers total. Okay, so I thought, okay, what's going on here? Is it so obvious that people don't write about it? Is it so obvious that people don't want to know about it? So I don't know. I just explored a bit and got some basic results. Okay, so here's my basic position. Shooting methods can provide an important function in exploring discrete boundary value problems, and there's 3 or 4 reasons why I think that. Right. Firstly, as you'll see, the method is very compatible with the form of discrete difference equations. Okay, so the technique is compatible with the problems. Secondly, it's easy to do, right? It's the mathematics is not hard. Okay, it's not hard to do. So I mean, even an undergraduate student or maybe a really good high school student could do this, in my opinion. Okay, and also you can get a number of different conclusions by using shooting methods. So for example, I have a history in fixed point theory, okay? And if you use a fixed point theory, most of the assumptions and the theorems involve sufficient conditions. And maybe they give you, I don't know, like Banach's fixed point theorem, they give you one solution. Well, shooting methods can give you much more. They can tell you there's no solution, there's one solution, there's 2 solutions, there's 15 solutions. So you can get a lot of different conclusions from using shooting methods. Okay, and so what I'm going to do is talk about, basically, this is just a fancy word for examples. Okay, exemplification. It sounds like really impressive in English, but it's just examples. All right. So here's the problem, and this looks a bit like what Andrea was talking about in her talk before. So I'm just using the basic forward difference operator, and you've got some maybe nonlinear function on the right hand side, and here you have some boundary conditions. Okay, so U, V, and W, they're just constants. Now, this is these are all sort of scalar problems. I'm just keeping it as simple as possible, but you could have matrices here, and this could be a system of equations and all sorts of stuff. But I'm keeping it as simple as possible. So you've got a difference equation, some boundary conditions, and later on I'll talk about sort of maybe some nonlinear boundary conditions if I have time. So that's the problem. All right. So here's the main result, and this is the only result I'm going to share with you today. Okay, but I'm mostly going to talk about examples. All right. So okay, so let me just put this back into the screen so we can hopefully see if I can. Yeah, I can get that in there. Okay, so you've got a function and you've got a parameter. What this theorem says it makes a connection between the solutions to your original problem and the solutions or the roots of this function here, okay? So let me just state the theorem for you. Suppose f is a real valued function, s is a parameter. The discrete boundary value problem here has the same number of solutions as there are distinct roots of this problem. So in other words, we're solving this equation here, where, well, what is this x thing? This is just the unique solution of the initial value problem. Okay, so it's very similar to what you see in ordinary differential equations, but in my opinion, there's an interesting twist here, because you can solve this initial value problem with almost no effort at all, right? You can write this as a recursion relation, and you can get the solution, right? So So all you do is you move this over here and you start with x naught equals s, and you can go through and get the solution, right? And then basically the challenge is to look at this problem and try to find the solutions. So if this has 3 solutions, then the original problem has 3 solutions. If this has no solutions, this has no solutions. Okay, so what we're doing is we're reducing the study of the boundary value problem to basically a simple, maybe transcendental equation. Okay. All right. So I'll show you some variations on a theme first. I think I just said them. So let me see if I can just push this in here. Yes. Okay. So if this has no solutions, then the boundary value problem has no solutions. If this has exactly 1 solution, then the boundary value problem has a unique solution. If there are j solutions, j number of solutions, then the discrete boundary value problem has exactly j solutions. To me, that's great, because that is much more than what a fixed point theorem can do. So some of you might know fixed point theory, and many fixed point theories, they give you a lower bound on the number of solutions. They say, oh, at least 3 solutions exist, or at least 1 solution exists, but they don't tell you the precise number. Many of them do not tell you the precise number. Okay, so they're the little variations on a theme. Okay, so I'll quickly talk about the proof. You can rewrite the initial value problem like this, and you just iterate, right? You just iterate. And you keep going until you get this in terms of the other parts, which is very easy to do. And then you can show that if S is a root of this equation here, then this also satisfies the discrete boundary value problem. Okay, so that's not hard to do, because the equations, let me see if I can find it. The equation, the difference equation is the same. It's just that here's the initial condition, and the boundary value problem has a boundary condition. Okay, so you're just basically verifying that there. So you can show that this also satisfies the discrete boundary value problem. So basically, if S satisfies this, then this satisfies the boundary value problem, the discrete boundary value problem. And you can go the other way, okay? Every distinct root of this phi function will yield a distinct root to the discrete boundary value problem, okay? And you can show that, well, just arguing by sort of contradiction, if you like, S1 and S2 are distinct roots. You can show that the two solutions can't touch. Okay. So last step, and then I'll do some examples. So we're going the other way now. So if this satisfies the discrete boundary value problem, then we can obtain a root of our phi function. And so you can go through and show that without too much trouble. Okay, so we've sort of done it both ways. I've rushed a little bit there. Maybe I'm not being so relaxed with the proof, but I really want to show you the examples. That's probably the most interesting part of this talk. Okay, so what? Well, it's a good question. Thank you for asking. The initial value problem is completely solvable by iteration. So what that means is it's very easy to get this. Okay, so you're given U, you're given V and W, you can compute that by iteration, and then all you're doing is looking to solve that equation. Okay, it's very easy to do. And if you compare that with the differential equations, sometimes even solving the initial value problem is quite difficult. Okay, if that's your function there, you can't integrate this in terms of elementary functions. So even solving the initial value problem with a parameter is quite difficult. Okay, so this is one big advantage that difference equations have over differential equations, in my opinion. Okay, so this is what I mean when I was talking about the compatibility between the methods and the type of problems that we're looking at. I think shooting methods are very compatible with these discrete boundary value problems. Okay. You can also do it with nonlinear boundary conditions. So in, let me see if I can find my slide again. Just give me a second. Yeah. So instead of these linear conditions, you can also form a theory with these nonlinear conditions. It's not difficult to do. Okay. Yeah. So that's not difficult to do. Okay, so let me give you some examples, because most people learn from examples, and I'll discuss 2 or 3 examples with you, and then I'll open the floor up for questions. So let's talk about non-existence, when no solutions exist. So here we've got a nonlinear problem. It's autonomous. You've got some linear boundary conditions, and I'm just making the interval really, really small, just to make it as simple as possible. Okay, so you can set up your initial value problem with a parameter S, and you go through and you iterate, and this is your phi function that you're looking at. Okay, it's this, and obviously we're squaring things and adding positive things here, so it's always positive. So this obviously has no roots. So by our theorem, this problem here has no solution. Okay. Now, of course, you could do this in other ways, but I'm just trying to illustrate the theorem here. Okay. So that's one example. What about 2 solutions? Well, I'm glad you asked. Same equation, different boundary conditions. Okay, well, you set up your iteration and you get something like this. And what you can do, let me see if I can bring this up on the screen. Can you see my graph now? Yep. So this is just GeoGebra. So you can see, oh, there's 2 solutions there. So the original boundary value problem has exactly 2 solutions. Okay, I feel like I'm on a roll. You can do the nonlinear boundary conditions as well. What happens in that case? 1 solution. Okay, 1 solution. Existence and uniqueness? Sure. Sorry, no, I messed that up. That was 2 solutions. I didn't do a graph for that. I got my graphs mixed up, sorry. So this one has 1 solution. All right. And finally, what about infinitely many solutions? Well, you do the same thing. Here's your boundary value problem. You set up your iterations. What happens in this case? Well, there you go. So I'm kind of converted now, because I used to really love fixed point theorems. I still do, but these shooting methods are so good. They're so good. So that's pretty much all I have to say. I told you it would be a relaxed talk, so I wanted to have a bit of a time for questions and maybe a short conversation about any ideas you might have or questions you might have. So let me stop sharing, and I should be back now. So Samra, I'll throw back to you if you want to go back for questions, or
Okay,
if anybody wants to put anything in the chat. I'm happy to. I hope everyone's enjoying the Olympics. If you've got any questions, just let me know. What do you think? Is it too simple? The paper was published in the Journal of Difference Equations and Applications, so it can't be too simple, I guess. So what do people think?
Well, we'll ask the people. Is there any questions or comments or maybe remarks for Christopher? I enjoyed your presentation, really.
Samra, there is a question, a raised hand by Magdalena.
Yes, Magdalena, go ahead.
Thank you. Good morning or hello to everyone. I have one question. Because you presented the shooting technique for discrete banded interval. So can you use for half-line, for BVP on half-line?
It's a really good question. Thank you, Magdalena. I haven't thought about it. The ideas for me are still quite new. So I'm still learning as I go, so that would be interesting. One of the challenges with a longer interval is you need to do more and more and more iterations. I mean, it's obvious, right? So that would be something to think about. In my examples, it's really like the interval's tiny. So I guess a question here is, how does, if it's an infinite interval, how does that affect the applicability or something like that? But yeah, that's a really good question. Do you have any suggestions?
No, I usually work on half-life, so I was interested in this because sometimes in differential equation, when we use shooting method for half-line too, to get some information when we have, thanks to shooting method, we can't find in differential equation, we can't find the solution we need, yes? So this question was because of this, yes?
That's super interesting. If you could share some papers or links with me, that would be really helpful, because I feel I could learn something there. That would be great.
I try find and send you, okay?
Awesome.
So thank you.
Thank you.
Thank you. Anyone else? Some comments, maybe? Okay, I'll thank again Christopher for a very interesting presentation and great talk. And we are going to our next speaker. The next speaker is Charles